Please join me in welcoming Wiebke HUTIRI, who is going to talk to us about responsible design of Edge AI.
Thank you for the introduction. HUTIRI, and I am wrapping up my PhD at Delft University of Technology in the Netherlands. It is my pleasure to be here today, and I particularly appreciate the welcoming and friendly atmosphere that the tinyML Summit has been so far. This is the Edge AI dream. The sun shines gently on a world built for cars, serene driving experiences without annoying co-drivers, no soul in sight, highways without traffic. Unless you collected your training data in March 2020, just after the COVID lockdown started, the reality is, of course, quite different. What then could possibly go wrong when developers' dreams and reality do not match up? Turns out that an awful lot has been going wrong over the past decade. In fact, the reliability and robustness of AI has been challenged on so many levels that it is worth pausing for a moment to ask, what if? What if your sister, your wife, your daughter yells, "Stop!" in panic to halt an autonomous vehicle, but her high-pitched voice fails to trigger the keyword spotting system as intended? What if you could have picked this up during system development, but you didn't because you never checked and no one ever asked? Now, getting to the root cause of AI failures is not a simple task, and not one I claim to be able to address in a short talk. But standing in front of you today in Silicon Valley, where dreams can still become a reality, I'm hopeful and dare to dream. What if we embraced responsible design of Edge AI as the tinyML community to do our best to prevent these kind of failures in future? But what is responsible design anyways, you might ask? I like to keep things simple. At its essence, responsible design is about recognizing the impact of how we design and ensuring that the products and systems we design align with what society values. Responsible design shouldn't be a new concept to developers and engineers. After all, elevating the value of safety has dramatically reduced fatalities in the mining and transport industries, or designing for sustainability is reducing the environmental footprint of manufacturing and the construction industries. Nonetheless, aligning design with what society values is difficult because societies value many things. Across cultures, one of the things societies value is fairness. One of the theories of why fairness matters is that it has emerged to enable human cooperation. When it comes to fairly sharing resources, there are two flavors of fairness. The first, which is considered more universal, is that people avoid being put into a position of disadvantage. The second is that people avoid putting others into a position of disadvantage. That said, judgments of what is fair can vary widely, and people often find explanations to justify their own positions. Despite these diverse perspectives on what is fair, humans have been able to find common ground on some things. The Universal Declaration of Human Rights is an example of this. In particular, I want to draw your attention to Article 2, the right of no discrimination, which entitles everyone to the rights outlined in the Declaration, without distinction of any kind. So what does all of this have to do with AI? Turns out that AI is not uniformly good at making predictions. AI prediction errors have a tendency to lead to unfair outcomes and discrimination. One of the sources of unfair prediction errors is bias. In its simplest form, bias refers to a skewed or slanted perspective. Typically, that skewed perspective is not neutral. Bias becomes problematic when it systematically assigns undesirable outcomes or denies opportunity or goods to individuals or groups based on grounds that are deemed unreasonable or inappropriate. Many machine learning engineers that are aware of bias view it as a data problem, but in reality, that's only part of the story. Bias enters machine learning products at many different stages in the workflow. Historical bias replicates biases like stereotypes that are present in the world as is or was. Representation bias underrepresents a subset of the population in its sample, resulting in poor generalization for that subset. Measurement bias occurs in the process of designing features and labels to use in the prediction problem. Learning bias concerns modeling choices and their effect on amplifying disparities across samples. I can actually show, there we go. Optimization bias is a specific type of learning bias that arises during on-device machine learning when modifying models to meet the resource constraints of edge and end devices. Evaluation bias is attributed to a benchmark population that is not representative of the user population and to evaluation metrics that provide an oversimplified view of model performance. During evaluation, aggregation bias is also of concern as it arises when data contains underlying groups that should be treated separately but that are instead subjected to uniform treatment. And lastly, deployment bias arises when the application context and usage environment do not match the problem space as it was conceptualized during model development. These biases are not static, standalone occurrences, but exist as feedback loops. We know that quite well from voice assistants, where people with accents don't use them because they don't work. So the data is never collected and used for training, and voice assistants continue to work poorly for them. In tinyML applications, bias is particularly problematic because our applications are pervasive and tightly coupled to the physical world, in homes, schools, and public spaces, where unobserved bias then poses risk of large-scale exclusion and discrimination. So bias in ML is a wicked problem, yet building unbiased tinyML is difficult, probably actually even impossible. However, that doesn't mean that we can't do anything about it. In fact, this is exactly why responsible design and recognizing the impact of how we design is important. We can take steps to reduce bias by detecting it, by taking mitigating actions to reduce its impact, and by communicating the limits of the applications that we build. Now, before you get too excited about doing that, detecting and mitigating bias in Edge AI is currently not so easy. There's a lack of transferable knowledge on how to go about it and limited awareness on how to apply established know-how and best practices developed in machine learning fairness. Those that dare to dive into algorithmic fairness research can find it difficult to navigate and prioritize. What results then is that well-intentioned efforts to detect and mitigate bias often end up being ineffective and counterproductive. For example, bias evaluations often fail to consider how biased products affect people, what should be measured to determine bias, what the limits of metrics are when measuring bias, and which comparisons to make to determine bias. We end up with evaluations that measure something, but it's not clear what they measure and why they measure it. This is why I've developed design patterns for detecting and mitigating bias. A pattern is an idea that has been useful in one context and will probably be useful in others. Design patterns for detecting and mitigating bias capture experience from machine learning fairness in a general way so that it can be reused in new Edge AI products. The patterns are categorized by their purpose, which is either for analysis or design. On a second axis, the patterns are categorized by scope. The scope roughly corresponds to the stage of the machine learning development cycle where they are applied. Dataset, evaluation, and interaction patterns are primarily used for analysis and bias detection. Pre-processing, in-processing, and post-processing patterns are primarily used for design and bias mitigation. Let me give you an example. The label distribution across groups pattern is a dataset analysis pattern that states that the label distribution of a dataset should be analyzed to ensure labels are balanced across groups. Why does it matter? Imagine you have a keyword spotting dataset in which you have carefully ensured that it contains an equal number of data samples from males and females. However, it so happens that the target labels for females only include the keyword yes, while the target labels for males include the keywords yes, no, and stop. So balancing samples only on gender is not necessarily sufficient to ensure a representative training data set. The patterns can be grouped together into recipes. Recipes help tinyMl developers to take the basic steps to conduct state-of-the-art bias evaluations. For example, the benchmark evaluation dataset recipe combines patterns to ensure that the benchmark datasets used for evaluation are representative, appropriate, and sufficient. The recipe consists of 5 patterns: evaluation datasets, metadata approximation, label distribution across groups, data quantity distribution across groups, and data source. In the interest of time, I won't go through all of them now. So while I developed the design patterns by learning from best practices in machine learning fairness, tinyMl applications have unique challenges that are not accounted for by cloud-based approaches. We have thus been looking for additional design patterns that specifically consider tinyMl design choices, context dependence, resource constraints, and optimizations. In a new empirical study that collaborators and I show that the data sample rate, input features, and pruning affects keyword spotting performance disparities between male and female speakers. While differences are only slight at 16 kHz sample rate and with a standard convolutional neural network architecture, performance disparities are amplified if the sample rate is reduced to 8 kHz and a smaller architecture is used. While these differences are not that pronounced if we only ever use Google Speech Command's dataset to train and evaluate, they become very evident on multilingual data. When taking a closer look at these results, we found that the input feature type and dimensions impact accuracy and bias. Generally, MFCC features perform better than logML spectrograms, but they also tend to increase bias, favoring male speakers over females. For pruning, we found that small learning rates at sparsities over 50% lead to dramatic accuracy drops and also dramatic increase in bias. We hope that this research lays the ground for future work on bias and robustness in tinyML. So to round up, design patterns are a tool for responsible design practice that helps organizations avoid costly mistakes, both financial and societal. Using design patterns can help tinyML engineers detect and mitigate bias more effectively, get up to speed with know-how on bias faster, develop a common language so that teams can talk about bias with each other and their stakeholders, and surface design alternatives and choose between them. From responsible design practice and recognizing the impact of our design choices towards building edge AI that aligns with our societal values of fairness and non-discrimination. Our next steps are to integrate patterns into tinyML development workflows, to implement the patterns in bias detection software, and to expand the application of patterns beyond our initial prototypes and speech systems. We are looking for first movers in the tinyML community who care about responsible design and are interested in piloting the design patterns in use cases with us. If that's you, come find me during a break or lunch and let's chat more. Thank you.